Quantum mechanics is full of strange ideas, but few are as mind-bending as quantum tunneling, the ability for particles to slip through barriers that should completely stop them. It sounds impossible, almost magical, like something only science fiction would dare to imagine. And yet it's happening right now, everywhere in the universe, inside every atom in your body, and even inside the sun itself. Quantum tunneling is one of the most important processes in physics, but it's also one of the hardest to picture. So today we're going to break it open with the simplest possible explanation. No complicated math, no dense equations, just clear ideas, intuitive metaphors, and a story that makes tunneling make sense. Quantum tunneling is one of the strangest ideas in physics. It's the kind of idea that sounds like it belongs in a science fiction movie or a fantasy story. Particles passing through walls, matter leaking through barriers, and tiny objects teleporting from one side of a divide to the other without ever breaking the barrier itself. But the truth is even stranger, because quantum tunneling isn't fiction. It's real. It's happening everywhere all the time right now as you listen to this. And without it, the universe as we know it wouldn't work. Today we're going to peel back the layers of quantum tunneling. We'll look at what classical physics predicts how quantum physics breaks those rules, what wave functions actually mean, why tunneling doesn't violate any laws, and why the sun itself relies on this process just to shine. And by the end, you'll see why tunneling isn't a weird loophole, it's a fundamental feature of reality. Let's begin with a simple question. How can something pass through a barrier without breaking it? First, let's look at the world through classical eyes. The world we're used to. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to climb over the hill, it rolls back. Simple. Or imagine pushing a box into a wall. If you don't push hard enough to break the wall, the box just sits there. In classical physics, barriers are absolute. If an object doesn't have the energy to overcome the barrier, it stops. The rules are clean and predictable. But the quantum world is not clean and predictable. At small scales, particles don't behave like tiny billiard balls. They behave like waves of probability. And because they are waves, they can do something extraordinary. Part of their wave can leak through a barrier. Not break it, not smash it, but leak through it. To understand how that works, we need to rethink what a particle actually is. In quantum mechanics, a particle is not a tiny point bouncing around like a miniature planet. A particle is a wave function, a mathematical object that describes the probability of finding the particle in different places. If you could zoom in far enough, you wouldn't see a little sphere. You would see a cloud, a smooth distribution of possibilities. Sometimes the cloud is tight and narrow. Sometimes it spreads out. Sometimes it overlaps several locations at once. And unlike a classical object, this wave function doesn't suddenly stop when it hits a barrier. It fades gradually like light shining on fog. Now imagine this wave hits a wall, a barrier. Most of the wave reflects, but a small part continues into the barrier, weakening rapidly. And if the barrier is thin enough or low enough, a tiny fraction of the wave emerges on the other side. That tiny tail of possibility becomes meaningful, because the moment the wave appears on the far side of the barrier, the particle can appear there too. This is quantum tunneling, the particle showing up on the far side of the barrier, even though classically it doesn't have the energy to cross it. It hasn't broken the wall. It never smashed through. It simply appeared on the other side because part of its probability wave existed there. And this is the essence of tunneling, not breaking, but leaking. But how does this make physical sense? How can something go from one side of a barrier to the other without passing through it in the classical way? The answer lies in the nature of quantum systems. In quantum mechanics, the position of a particle is not a single definite point unless you measure it. Until you observe it, its wave function spreads over multiple places. The barrier doesn't force the wave function to stop abruptly. So mathematically, there's always a small but non-zero probability that the particle will be found on the far side. If the probability is non-zero, the event can happen. And when we look, sometimes it does. Let's make this even simpler, because tunneling sounds magical only if you imagine particles as little balls. But if you imagine particles as waves that don't instantly disappear, then tunneling becomes exactly what you'd expect. Waves leak. Waves bleed into regions you might think they shouldn't enter. And once part of that wave exists on the other side, so does the chance of the particle itself being found there. Here's a simple analogy. Imagine shouting at a thin wall. Most of your voice bounces back, but some vibration passes through. On the other side, the sound is faint, but it's there. Quantum tunneling works the same way, but with probabilities instead of sound. Now let's step deeper. Why doesn't tunneling violate energy conservation? It might seem like the particle magically gains energy to cross the barrier, but that's not what's happening. The particle does not climb the barrier. It never rises over it. It simply appears on the other side because the wave function does not vanish completely. From the quantum viewpoint, energy is conserved because the particle never physically went over the barrier. It only existed on both sides with small probabilities. When you measure the particle, you collapse the wave function into one location. If you find it on the far side, that means the improbable side won. Quantum mechanics does not forbid improbable outcomes. It just gives them small chances. Think of a lottery. The odds are tiny, but someone wins. Quantum tunneling is the universe's version of winning the lottery, except it happens constantly everywhere. So now that we understand what tunneling is, let's explore where tunneling actually shows up. The first and perhaps most important example is the sun. Every second, the sun releases enormous amounts of energy through nuclear fusion hydrogen atoms, merging into helium and releasing light and heat. But here's the twist. The core of the sun is hot, but not hot enough for regular classical fusion. Classically, the atoms should repel each other so strongly that fusion could barely occur. But quantum tunneling makes it possible. Hydrogen nuclei don't have enough energy to overcome the electrostatic repulsion barrier, but their wave functions extend just enough for them to tunnel through that barrier. This tunneling is what allows them to fuse. And because they do, the sun shines. Without tunneling, fusion would be far too slow. The sun would go dark. Life on Earth would never have emerged. So in a profound sense, tunneling is the reason we exist. But tunneling doesn't just power stars. It appears in radioactive decay. Many atomic nuclei are stable until particles inside them tunnel through an energy barrier and escape. This is why certain atoms spontaneously emit particles, and why radioactive decay has specific half-lives that depend on tunneling probabilities. Tunneling also shows up in solid-state physics. Inside a crystal lattice, electrons can tunnel between energy states, allowing electrons to move through materials in ways classical models can't explain. This is the foundation of many electronic devices. In fact, tunneling is so central to modern electronics that entire technologies rely on it. Tunnel diodes, for example, use tunneling to operate at lightning-fast speeds. Flash memory uses tunneling to trap electrons in thin layers. Scanning tunneling microscopes. The tools that can image individual atoms work by measuring tunneling current between a metal tip and a surface. Without tunneling nanotechnology, as we know it wouldn't be possible. But perhaps the strangest part of tunneling is what it tells us about the nature of reality. It shows us that the universe is not deterministic at small scales. It's probabilistic. It doesn't decide outcomes until events happen. And even then, the outcomes are chosen from probability distributions, not fixed paths. When a particle tunnels through a barrier, there's no hidden force pushing it through. No secret energy, no invisible tunnel. The wave function simply extends into forbidden regions. And when you observe the particle, the universe chooses the outcome based on probabilities. This leads to a deep philosophical question. Is tunneling a sign that reality itself is built on uncertainty? Is the universe fundamentally a place of possibilities rather than certainties? Quantum mechanics suggests that it is. Let's make this picture even clearer with a final ultra-simple explanation. Imagine a particle as a wave. When the wave hits a barrier, most of it reflects, but part of it fades into the barrier and emerges slightly on the other side. If the barrier is thick, the wave barely gets through. If it's thin, more gets through. The wave doesn't break the barrier, it just extends beyond it. And wherever the wave exists, the particle can exist. Once you understand this, tunneling stops being mysterious. It becomes a natural consequence of waves. Now let's explore one more idea. Quantum tunneling is not rare. It happens constantly. Electrons tunnel inside atoms. Neutrons tunnel in nuclei. Energy levels in molecules depend on tunneling. And even macroscopic objects like you have wave functions. But the probability of you tunneling through a wall is so absurdly small that it might as well be zero. Not zero, but effectively zero. In the lifetime of the universe, you would never see it happen. Quantum objects tunnel because their waves are wide and fuzzy. Human bodies don't tunnel because our wave functions are impossibly tiny and narrow. At large scales, quantum behavior becomes smoothed out, and the classical world emerges. But the classical world is just the quantum world averaged over billions of particles. Everything, every atom, every molecule, every star is governed by quantum laws. And tunneling is one of the clearest signs of this hidden quantum foundation. So why does tunneling matter? Why should we care about particles slipping through barriers? Because tunneling is a window into the deep structure of reality. It shows us that the universe is not solid. Barriers are not absolute. Particles are not points. Energy is not fixed in place. And the future is not always determined. Tunneling is a reminder that nature doesn't follow our intuition. It follows its own rules that are often stranger and more elegant than we expect. Without tunneling, atoms would behave differently. Stars wouldn't shine. Technology wouldn't function. Radioactive processes wouldn't occur. Chemistry itself would be transformed. The universe we know is built on a foundation where the improbable happens constantly. So the next time you hear that particles can pass through walls, don't imagine magic. Imagine waves leaking through barriers. Imagine possibility leaking into forbidden spaces. Imagine a world where the improbable becomes routine, not because physics is broken, but because this is how physics works at the deepest level. Quantum tunneling isn't a glitch in the universe. It's one of its fundamental features. And once you understand it, the quantum world becomes less mysterious, not more certain, but more understandable. And that's how quantum tunneling really works. Quantum tunneling shows us something profound about the universe. That reality isn't rigid. It's flexible, fuzzy, probabilistic, and far more surprising than the world we see at everyday scales. Barriers aren't absolute. Particles aren't fixed points. And the impossible becomes routine once you zoom in far enough. Without tunneling, stars wouldn't shine, chemistry wouldn't work, and modern technology wouldn't exist. But because the universe allows probabilities to leak through barriers, everything around us, including life itself, becomes possible. If you enjoyed this breakdown and want more simple, story-driven explanations of the hidden rules that shape our world, feel free to subscribe and join us for the next exploration. Until then, stay curious, because in the quantum world, even the smallest possibilities can change everything.